Topic 2, redox. Everything comes down to redox it's just a smushed form of the words reduction and oxidation. Oxidation when something loses electrons, reduction when something gains electrons. So probably helpful to remember the thing oil rig, right? Question? Yes. Yeah. So probably helpful to remember the acronym oil rig. So oxidation is loss, reduction is gain. Yep. Cool. Oxidation or redox, the first thing is about oxidation numbers, and this is really important. I will spend a couple of slides going about this because the oxidation numbers is like the fundamental bit of all of this. So, oxidation numbers is all about quantifying the loss and gain of electrons, right? I'm just going to basically read the slides because I've covered everything here. Oxidation numbers can be given to all the elements in a molecule, right? So if I had H2O, I can give it to all the H's and all the O's. Changes are written in order of number. So charges are written in order of number first, then the sign. So I had maybe like SO4 2 minus, right? I wrote a number first, then the charge. Oxidation numbers are sign first, then number. That is a big difference. You have to get that right. So maybe the oxidation number for copper or something might be +2, right? Versus the ion being Cu. So let's say Cu 2 plus. The charge is this. The oxidation number would be +2. Big difference, right? Cool. Other round, it's just wrong. Transition metals, it's sometimes given. Iron 3 ion, the 3 here tells you the oxidation number is +3, right? Cool. For ionic compounds, the oxidation state, or the oxidation state number, whatever, is the number of electrons they donated. So if I had MgCl2, Mg is -2, Cl is +1, right? This is group, what is that? Group 2, and this is group 7 or something. I don't know. Yep. This tells you the number of electrons, that is oxidation number. Yeah. Cool. More on oxidation numbers. The sum of all the oxidation numbers in a molecule is the same as the net charge of the molecule. So if I had SO4 2 minus, I have this is a polyatomic ion. If I found the oxidation number for oxygen, for all 4 oxygen, so 4 times whatever oxygen is, and I added it to the oxidation number of sulfur, I should get -2. The sum should be the charge. That is really important. And if I have a neutral molecule, so let's say I had CH4, right? Methane. Should I probably working out for this? I think everyone has their own different way of working it out. I'll show you what I do for one of them. I'll do an example for you later on. But yeah, and a working out there. Yeah, I think it's okay to just put it. So yeah, stage 4. The sum of all the things here should equal 0 because there's no charge, right? Okay. So here's an example: iron 3 oxide, Fe2O3. The oxidation number for iron is +3 because I told you iron 3. So there you go, iron 3. Compound is neutral. I've written that. So the net should be 0. If there are 2 for each iron atom, there is Fe2 contributes total +6 because +3 times 2. So therefore the total of O3 must be -6 because +6 minus 6 has to equal 0. Why are we doing math? But yes. Yeah. O3 must be -6, so each oxygen is -2. Cool. Molecules made of one type of element are always 0 in oxidation number for each atom, or let's say for each element. Element sounds nicer. For example, the H in H2, each H is 0. The S in S8, each S is 0. Yep. The oxidation number for oxygen is almost always -2. Almost always. There are some exceptions. There's any peroxide is different. and any superoxide. I literally only learned this while I was researching. Is S8 a real compound? Yeah, I'm pretty sure it is. Um, uh, superoxide, I believe, I only just found it out. I've literally never seen this, so don't worry about that. I've only seen one peroxide ever, and that is hydrogen peroxide, H2O2, where each hydrogen has an oxidation number +1, and each hydrogen is +1, each oxygen is -1. Right? Panda is very insightful. Panda is mine. It is a lot of effort. Um, so yeah, oxygen number is basically almost always -2 for oxygen. Cool. Uh, polyatomic ions and or a salt of polyatomic ion. The net oxidation number within a polyatomic ion should equal the net ion charge. We kind of already saw this earlier, but remember the formula book can help us figure it out. So here is sulfuric acid, H2SO4. I want to figure out S in this whole molecule. Obviously, I guess I can say this whole molecule has to sum to 0, but I can do even one better. SO4 2- is a polyatomic ion. This is a sulfate ion, right? I wrote it here, sulfate ion. Oxygen is -2, because it is, and it's H2O2. Yeah. Oxygen is -2. 4 oxygens will contribute -8. Because I need the total of this ion to be -2, then the sulfur alone must be +6, because +6 -8 equals -2. You can have other peroxides, but I've not seen any of them ever, and I've only seen hydrogen peroxide like once ever. Yeah. So yeah. Yeah, even hydrogen peroxide coming up is very unlikely. Hydrogen peroxide, no. Hydrogen peroxide is H2O2. Hydrogen is +1, oxygen is -1. Yeah, cool. That the one you gave us in the external? I hope not. We had a question like that on my school's mock. That's actually where I got that question from. Uh, but I think no, Panda. I think if they give it, they will scaffold it. They had something similar in the past, but they scaffolded it. Yeah, that's the biggest difference. Yeah, I hope so. So, uh, last slide on oxidation numbers. This is purely about hydrogen. If hydrogen bonded with a non-metal has an oxidation number +1. So if you look at H2O, O is a non-metal, so oxidation number +1, oxygen is -2. Kind of already know both of those now. If hydrogen is bonded with a metal, it has an oxidation number of -1. So in sodium hydride, NaH, it takes it takes -1, sodium takes +1, right? And remember, this is because this is an ionic compound, and sodium would prefer to give away that electron, right? Hydrogen's in that weird spot. If you actually look at it, hydrogen's in a weird spot where it can either gain an electron to get a full shell, or it can lose an electron, and now it's got it's also stable. So it can really go either way, and this is why. For completeness about hydrogen, if H is in H2, then it has an oxygen number of 0, right? Um, cool. This is some questions about oxidation numbers. You can have a go at this. I'm not going to do all of them. Someone want to see my working for it, so I will do. Let's just take KMnO4 minus. So if I take KMnO4 minus, wait, not minus, sorry, KMnO4. Yeah, my bad. MnO4. The reason I had that in my mind is because MnO4 minus. I know oxygen is -2, so I'd like to write. Again, the working really doesn't matter, but like to write this is -8 because there's 4 of them. So therefore, this is +8. Sorry, +7. +7 -8. Playing Clash. And because it's a neutral molecule, this should be +1. Hopefully that all makes sense. If you want to take a screenshot of these, have a go at these. Some of them should be really easy. Some of them, I guess, are a little bit trickier. Yep. Fe3O4 is a good one if anyone wants to try. That's a nice one. But yeah. Cool. Moving on. Identifying redox. So a chemical reaction is said to be a redox equation if in the equation, or in the reaction, one species gets oxidized and one species gets reduced, right? How we figure these out, oxidized and reduced, I'm going to explain literally on the next slide, so don't worry about that yet. Yeah, I'm glad you guys are having fun with Fe3O4. Yeah. Species oxidized is called the reducing agent because it has the power to make the other thing undergo reduction. Right? Sometimes you hear it called a reductant. That is another way to say it. No one gets it? No, I'm pretty sure. What 8/3? I'm pretty sure is right. It's a not whole number, and the reason being, it is. Uh, I'm pretty sure. I will. I will. I mean, I'll have another. I will look. Uh, Oxidation. Oh no, it does some weird. Maybe I gave you a stupid question. That might be my bad. Let me have another look-see. Yeah, but that doesn't balance out. That's what's tweaking me. No, I looked at a source, I swear. Wait. Let me screenshot this. Hold up. I swear I wasn't tweaking. Unless this guy is lying to me. Yep. It's a fractional oxidation state. Yep. I don't know what AI is telling you, but yeah. Yeah, it does some weird thing. It's a little confusing. I technically never told you that it had to be an integer, so different oxidations. The chemistry is not real. I'm glad you guys are having fun. Let's continue. Kind of non-integer electrons. You know, who knows anymore? Oxygen is -2. That is correct, but the oxidation state of iron should be a fraction. Yep. Cool. Moving on. Species gets oxidized is the reductant. Species that gets reduced is called the oxidizing agent or the oxidant because it has the power to make other things undergo oxidation. It is very confusing. You just got to know it. That is game is game. That's it. You guys are still talking. My externals are over. That is very true. I'm glad you guys still have. Why are we still on Fe3O4? So let's do Fe3O4 because it's been a big discussion point in the chat. Fe3O4. If this is -2, this will be -8. So this should be +8. So this should be +8/3. Fe3O4 is actually kind of common. I forgot where, but yeah, cool. Seems so odd. Yeah. Cool. Sorry. Uh, what I was going to say was, or what I was saying is, we said that it's redox if one species is oxidized, one species is reduced, right? Yeah, no, I think I muted myself, right? I accidentally muted. Should be back. Wait. Yeah, I'm back. Um, so one species is oxidized, one species is reduced. How do we quantify that? How do I know if it's reduced? How do I know if it's oxidized? Well, oh, it just lagged. Okay. A species is oxidized or undergoes oxidation if the oxidation number is more positive on the product side than the reactant. So it increases from left to right. It goes up, right? That is oxidized. Well, by the exact same logic, it is reduced, undergoes reduction if the oxidation number is more negative. So it goes down, right? English theory you don't chem. Honestly, chem's worse. I was literally so what when can I drop it? um we will get there eventually. You can also put it in the help channel and I'll get to it after. But yeah, if I have time at the end, I will just take questions openly. Yeah. So what about this one? Well, this is oxidation number 0, this is oxidation number +2, this is 0, this is +2. So copper decreased in oxidation number from +2 to 0. And we said if it decreased, then it undergoes reduction. And, oh wait, yeah, sorry, I kind of skipped zinc. And zinc increased from 0 to +2, so it goes up. And so it underwent oxidation, right? Another way to think about it is oxidation is loss, if you remember your oil rig. So if zinc lost electrons, it's losing negative charge. If it's losing negative charge, then it should be becoming more positive. And vice versa for copper. Copper is gaining electrons because its reduction is gain. So copper is gaining electrons, so it's gaining negative charge. So the positive +2 will go to 0, right? Hopefully that makes sense. Half equations. So half equation, this is simple condition. We're going to learn in acidic conditions later. But half equations, we basically just take the thing that's getting oxidized and we just shove it into an equation. And we just add electrons to balance it, right? We will do an example for half equations. Do not worry. Zinc 2 plus, and we have 2 electrons that balance charge. How do you half equations in acidic? We will get to that. Don't worry. No. Cool. They are in fuel cells. That's unit 4, fortunately. But yeah. Then copper to this. This is our reduction half equation. We are adding the electrons here to balance the charge again. So this is a -2 charge. This is a +2 charge. This is 0 in charge. Yeah, it is. Galvanic and electrolytic cells, I believe, are unit 3. Fuel cells, I think, are unit 4. I don't know why. I think my school taught it in unit 3 as well. It's all redox. Yeah, I don't know. Anyway. Anyway. Finding half equations. Still similar condition. This is our oxidation reduction. I already wrote those. You don't need to state symbol for the electron. It is what it is. Charge on the opposite side should be equal. So if I didn't have this electron, this is charge of +2, 0, this is charge of +2. So I need a -2 charge to balance it out. That comes from my electron, right? If I've done it correctly, reduction half equation should have electrons in the reactants, and the oxidation half equation should have electrons in the products. So this is my oxidation half equation. The electrons are on this side because it is losing electrons, right? Electrons gassy. This is my reduction half equation. It is gaining electrons, so it is on the reactant side. They are these. If you turn them in master class, they are being recorded. I don't know. It'll be posted eventually. So same thing. This is another case. This is lithium and barium. This is 1 electron, this is 2 electrons. Here we were looking at if I have one equation, I want to find the half equations, right? I'll have to look at it later. This is starting with an equation, we want to find the half equations. What if I have the half equation, I want to find the full equation, right? We're just going the other way around. So this is one equation, this is one equation. Hopefully you realize this is oxidation. This is showing the loss of electrons. This is reduction. It's showing the gain of electrons. Reduction. I should have written oil rig in the corner of every slide, but oil rig. So the way we do it is we want to add the two equations together, and then we want to cancel out all the common terms. So we want to get rid of electrons specifically. We don't want any electrons in our reaction when we add them together. So I'm going to take this first one. I'm going to double it. So we took this, we doubled everything. I have 2 lithium, 2 lithium, 2 electrons, right? An Oxford cat. We double everything. And then I'm going to add my two equations together. So this one and this one. And I add them together. This is everything combined. And I'm going to remove all the same molecules. So I subtract the 2 electrons from either side. I don't think I've heard fat cat. What's fat cat? Anyway. And we get this, and this is our final equation. From anode to cathode. Ah, I see. Interesting. Is this one redox, and why? Have a quick think. There's only really one molecule that's tricky. And I want you guys to tell me, is this redox? Cool. I'm getting a lot of answers. This one is, in fact, where the rest of the things gone? What do you mean? This is in fact redox. Yep. Just let's think through it for a sec. Cr2O7 minus is a polyatomic ion, and it has a charge of -2. Right. Let's just double check that before I'm tweaking. With potassium. It's not balanced. That's correct. It's not balanced. -2. Thank you. Okay. It is not a balanced equation, but it is an equation. We're going to do this with oxidation state. So it's -2. For some reason, I ended up checking it myself anyway. Chromate Cr2O72 minus. Cool. This is -2. Those italicized. It's because I did it in the word equation, so it's now italicized, and I couldn't be able to change it. It is in fact still going. We are going for a while. -2. Each. Let's just look at this. This is -2 minus. This is -2. This whole thing is -14. So this should be because it's 2 minus. So this should be +12. So this should be each one should be +6. So 6 to 3, 2 to 3. So one of them gets reduced, one of them gets oxidized. And this is cool and all. We know this is redox, but it's not balanced. And I want to figure out how to balance it. And this one can only be balanced in acidic conditions. And there's a lot of steps. I'm just going to put this on screen, and then I'm going to do a full example of this by itself. Right? Yeah. Acidic conditions. So, if you want to take a screenshot of this, I'm going to go off this slide for a sec. So if you're curious, you can take a screenshot. Equal techniques, things unit 4. Is this redox? We're balancing it too. So you can take a look at this, take a screenshot if you need. I'm gonna go through this. I'm gonna say all the steps. So first, I want to let's write the reduction half equation, right? You will need to balance yourself, yes. Let's do the reduction half equation. Reduction is when we gain electrons, and we're gaining electrons between this molecule and this molecule, right? The Cr goes from +6 to +3, so we've gained electrons, right? When we write the reduction half equation, you will only take the this is an ionic compound. We get rid of this because this is this can dissociate, we get rid of this, right? Acidic condition, these are aqueous, by the way. That's important. That's why we can get rid of it. This is ionic, we can just get rid of it. It's not related, right? So we have Cr2O7, Cr2O7 2 minus, O7 2 minus. Let's put it in the middle. Cr2O7 2 minus become Cr3 plus. Okay, very clearly not balanced still. What do? First step, we will multiply any of these terms to make sure all of the elements that are not oxygen and not hydrogen are balanced. So here we have 2 chromiums, and here we have 1 chromium. So 2 chromiums, 1 chromium. So I want to multiply this by 2. Now the number of chromiums on each side is balanced. Cool. Next step, I will add water, and I will just add water molecules to either side until all of the oxygen is balanced. So here I have O7 here, so I need 7 H2O to balance it. Cool. Next step, I want to add H plus ions. The reason I can add H plus ions is because it's acidic conditions. That is the whole point of this. Electrons are last. Oh, you don't know me, my bad. Then I will add H plus ions. So here I have 14 hydrogen ions here. So I will add 14 H plus ions on this side, right? Neutral, yeah. Wait, damn neutral solution. I'm not sure what you mean. This is an acidic aqueous, right? I'm going to add 14H plus. This is balanced. So now all the elements are balanced, but the charge is imbalanced. So here we have plus 14, minus 2, plus 6. We have 2 3 pluses. So the net here is plus 12, net here is plus 6. So I need 6 electrons on this side to balance it. Cool. That is this one balanced. That is my balanced reduction half equation. Again, the steps, if you've forgotten them, are here. They're just there. So, oxidation half equation. This one's a lot easier. Fe2 plus to Fe3 plus. There's one iron atom here, one iron atom here. That's balanced. Oxygen is balanced. Hydrogen is balanced on both sides because there are none, right? So the only thing we have to worry about is adding an electron, right? Nice and easy. So here are our 2 equations. We have oxidation and we have reduction. What's the next step? Well, we kind of already saw it earlier, but we want to combine them. And we want to combine them in such a way that there are no electrons, right? So here we have 6 electrons. I'm going to multiply this equation by 6. So I'm going to get 6Fe2 plus forms 6Fe3 plus 6E minus. Now I have 6E minus on the right-hand side and 6E minus on the left-hand side. So I'm going to add them together, right? I'm going to add this equation, I'm going to add it to this equation. And because I'm lazy, I'm just going to write on the next slide. This is it added together. There was 6E minus here and 6E minus here, but I've just cancelled them because they are the same on both sides. So that is that. That is a balanced redox equation in acidic conditions. Yeah, forget states as well. I'll quickly write it. States AQ, AQ. It's all AQ actually, except for water. Liquid and aqueous. Cool. Go over the titration stuff again. If we have time at the end, but I feel like we won't. Oh well. Okay. Is this equation redox? This is an interesting one. I want to see what you guys say. I've got an alternating answer so far. Maybe. 50-50. All on red. Yeah. So this is a bit of a sneaky one. This is hydrogen peroxide, and if you remember, hydrogen peroxide is a funny exception. This is right on this side. H is +1. This is -2. This is 0. Here, oxygen is -1, and here hydrogen is still +1. God, it's on the top of the slide. Obviously, it's disproportionation. um, so here we have oxygen. Oxygen is -1 here. No, so oxygen is a special case. Oxygen is, not oxygen. This is H2O2. This is hydrogen peroxide. In hydrogen peroxide, it's an exception to the rule. Hydrogen peroxide, oxygen takes an oxidation number of -1. It's an exception. Disproportionation is where, notice how oxygen here, it goes from -1 to -2, right? And it goes from -1 to 0, right? We have both here. We have a 0 coming from this -1, and we have a -2 coming from the -1. This is disproportionation. It is when the same element gets both oxidized and reduced. So from here to here is a reduction. I'll just write red. And from here to here is oxidation. This is a really weird one, right? This actually came up. Well, they didn't call it disproportionation, but a question of this type came up before. So you don't need to know the name if you don't remember it, but I just want to point out it can be the same element that gets oxidized and reduced. I didn't balance it, but you can. This is just the basic stuff. I was gonna have another break. We're not gonna have another break. I need to keep going. Unfortunately. You can take a screenshot. You can try that in your own time if you want, but I will keep moving. Give a bit of time for screenshots. Cool. Moving on. Metal displacement. We kind of already saw that. I had an example earlier, and now how far back it was here. Copper and zinc. Zinc can kind of just like give its electrons away, right? It just does that. And the way it does that is kind of special. Metals can just give away the electrons. It's just something they can do, right? It doesn't ask for basic conditions out of syllabus. Yeah. It kind of just gives its electrons away, and the way it does it is the more reactive metal will give its electrons away to the less reactive metal, right? So here I have a copper metal placed in a zinc ion solution, and here I have zinc metal placed in a copper ion solution. Obviously, only one of these can take place, right? But which one? And that's what I want to figure out. So I want to know which one is more reactive. And unfortunately, it is on your data book. I'm not sure what page it is. I'm sure you can find it. This is a reactivity series for metals. Yeah. When you're looking at electrolytic cells, you use a different page. You should be using this one, even though this one and the SEP table are basically identical, but they are slightly different. Coding works something similar. We will. I will go through those. Yeah. If I'm running very short on time. I'm actually gonna go over time. It's gonna go over 3 hours, which is kind of cooked. That's my bad, guys, but it is what it is. Over the overtime. Hopefully the recording doesn't cut off. Go until midnight. Loki, once we finish, I'll just sit here and I'll just take questions. Okay. So, let's look at this. We were looking at zinc and copper. We have zinc over here, copper over here. So clearly, because we have zinc, that is, zinc is more reactive than copper. So this one will take place. This one will not. So what will happen is zinc will give its electrons away. Zinc 2+ in aqueous solution. This is 2E-, and it'll give it to copper, and the copper will take it. We already saw this example earlier. I just want to reiterate it. To do with the reactivity series. Cool. When will this be posted? I don't know. Is this used for electrolytic products? If you mean like for electrolytic cells, we will get to that. Cells, surprise, we've gotten to it. Oh, this is galvanic first. So galvanic cells. There's just a bunch of stuff. I've kind of all just thrown it all at you because I don't know how else to approach it. um, so what happens is what we've done is this ability for zinc to give its electrons to copper. This is chemical potential energy. I don't want to go too much into physics, but this is chemical potential energy, right? And what we want to do is we want to harness chemical potential energy and turn it into electrical energy. Physics. So, what we're going to do is we know that zinc is capable of giving away its electrons to copper, right? So, we set up a contraption like this. We're going to take the zinc. Zinc wants to give away its electrons. It wants to turn into this and it wants to give away electrons, right? Which is the same, always left to right. It depends on how you draw it. Yeah. Yeah. So, here we have the zinc. Zinc is hooked up to this copper cell, right? The electrons, so here we have zinc metal. This is zinc solid metal, right? Remember, we had this example where the zinc was giving it to copper. We're now making the electrons go through a couple of steps, right? So, zinc is going to give away its electrons. It will turn into an ion and it will release the electrons. So electrons go through here, right? And the zinc will turn into an ion form. So here we have some liquid. Ignore the salt bridge for now, we'll get to it. Here we have some solution. It will release zinc into this solution, right? Then electrons will travel through here, right? They will go through this voltmeter. The voltmeter tells me potential difference. Which is a voltage. If you don't do physics, just remember it's a voltage. It tells me the voltage between the 2 points. That's all that matters. Electrons go through here, through here, through here, through here. And then the electrons go out. This is a metal. Metals are conductive, right? Are being released. Are these ions that are being released? The reason for the galvanic cell to be balanced. I'm not sure what you mean by balance. The salt bridge is what keeps it balanced, if that's what you mean. Calculate the magnetic field produced by half cells. Only you do. So electrons, they go here, they go out. Here we have some Cu2 plus. The Cu2 plus, they take in these electrons. Cu2 plus. Yeah, so we'll get to that. A Cu2 plus, it takes in electrons. Cu metal. Actually, I want to take a quick general poll. I mean, it's not really a poll. I just want to see you guys say yes or no to this. Would you guys rather we finish on time, or I take this bit a little bit slower? And oh no, okay, slower. We will end up going very over. Understand this bit? Yeah, I don't know how the recording's going. That's my worry. Record it again. I'm not the one recording, unfortunately. Johannesburg, are you able to somehow record or figure out a way for someone else to record or something? Basically, Johannesburg, can you just sort out the recording for me? So I don't have to worry about it? Okay. Okay. I think we've got a consensus. Who knows how long we... Okay. Who knows how long we'll go until... You don't have to do it if you can figure out another way to. I don't know. So, will you still get... Yes, you will still get the PowerPoint. Sorry, I'm back, guys. Do I offer tutoring? I do tutoring, yeah. Okay. Let me continue. My bad. So the electrons go into the copper. This is a copper solution. It has copper and some other stuff. Doesn't really matter. One-on-one private time. DM me about that. It will take in the electrons and it will form solid metal, right? He's fine. Hopefully that makes sense. So, is that bit? Ignore the salt bridge. We'll get to the salt bridge in a sec. Is that much clear with everyone? Does everyone understand that? Zinc is more reactive than copper, so the zinc will turn into zinc ions and will go into the solution. This is a liquid solution, and the electrons will go over to the copper half and they will be used there. But the electron will pass through a wire first, and that's how we'll measure it. Is that clear with everyone? Yep. No? Yes? Why did the person why are you called yes? Why is your username yes and you said no? What? Just I don't get it. I'll try and explain. Let me try and go through it again. We've got more time. So, restart. Holy rage, mate. Okay, zinc is more reactive than copper. So zinc wants to give its electrons away to copper, right? In this example, zinc and copper were just touching each other, right? So that zinc could just give it straight to the copper. 9 a.m. tomorrow. So zinc just wants to give its electrons straight to copper, right? That's fine. But what if we could harness that? What if we could take those electrons? What if we could turn chemical potential energy into electrical energy? What if for the zinc to give electrons to the copper, it had to go through a whole wire first? That's what we're doing with the galvanic cell. So, oh, I can't rub out again. There we go, I can again. That's what a galvanic cell is. So here we have zinc metal, right? Here we have zinc metal. The zinc is giving away its electrons, right? When zinc loses electrons, zinc is solid. When zinc turns into an ion, it has to become aqueous. Why? I don't know. It just is aqueous, right? It becomes aqueous. This is some liquid, right? It generally, it will already have zinc ions in it. That doesn't really matter for what I'm trying to say, but has zinc ions in it. It will give away its electrons, and it will turn it into an ion form, Zn2+, right? Then let's track these electrons. These electrons will go through the wire, right? They go across. They go into this. This is called the cathode, anode, cathode, right? They're just the names. You don't have to. They're just the names, right? At the cathode, whichever one is more reactive will be oxidized. Yes. But when we do these cells, you don't have to use this table anymore. We get a new table, an upgraded table, table of V2. Spoilers. We'll come back to that. So, the electrons here. Yeah, I was actually about to say, if you want to know, here's anox, red cat. So this is anode. Anode is oxidation, and you have cathode is reduction. Okay, back to this. Electrons, they go through here, right? They sit in this, and then in this, they will go out. Here there's some copper ions. The electrons here will be negative in charge, so they'll be negative, and the copper will feel an attraction to it, right? The copper ions will come close, and then the electrons will transfer it from E to the copper ions, right? Then what happens is copper ions will get the electrons and turn into copper metal. Does that make sense as an explanation? I forgot the person that asked, but we started with this. Say it again. Is the anode always oxidized, but it can be no, the anode is also always negative. In the anode is always anode is always negative for galvanic cells. It is different later. Yeah. Negative in galvanic. Positive in electrolytic. Yes, we'll get to that. Sorry. So what was I saying? So the short version, to quickly summarize this again, zinc is more reactive than copper. Zinc wants to give its electrons to copper. That's just it, right? The zinc will give away its electrons, and it will give it through this wire. It can't do it directly anymore like it could. Like here, it can't just send it directly from 1 to 1. But it can send it through the wire and into the solution, right? Yeah. And so it's sending it through the wire into the solution, into this here. It is going all the way through. That's how the electrons travel. Earlier, they just traveled straight 1 to 1. Now it's through a whole process. But they still go from 1 to 1, one to another. Right? And when it does so, the zinc has to turn into zinc ions. And when the copper gets it, the copper turns into solid copper. Do we need to know metal displacement? Yes, you do. Is that clear? Is everyone comfortable with galvanic cells up to here? Okay. They're single and double displacement, or something I don't know. Yeah. I don't have an example. If someone can get, I did see. So anode is negative, yes. What was I saying? I already lost. Double displacement. If someone has an example of a double displacement reaction, could you just send it in the chat? I don't have one off the top of my head that I can think of, but double displacement is a thing. It's where double displacement is where AB plus CD becomes AD plus BC or something. Something like that. Okay. Finally, or not finally, with galvanic cells, there's a lot on this. That's why I just put in a diagram. I want to talk about it. That's why I'm fine with spending a lot more time on this slide, just so we all get it. Yeah, thank you. If you look at this cell here, right? Over time, the zinc is going to turn into zinc 2 plus ions. So maybe let's say there's only a couple in here, right? There's not many zinc ions. But over time, it will become, there'll be more and more and more, right? What'll happen now is if this happens, this solution is highly positive. Very, very positive. There's a lot of positiveness, I guess, right? Then the electrons don't want to go this way anymore. Electrons are negative. They're attracted to positive charge. If this gets too positive, the electrons don't want to go. They just want to stay here, right? So what we can do is we have a salt bridge. And what the salt bridge does is this salt bridge is made of a negative ion and a positive ion. So a cation and an anion, right? The anion will slowly travel towards the positive solution. So in this case, Zn2 plus. It will travel to Zn2 plus, and it will neutralize it. It will go Zn2 plus, or not even that. There'll just be some negative ions here too. NO3 minus. It's a mess now, but you get the point. NO3 minus, and now it'll be fairly neutralized. Or not neutralized, it'll be neutral in charge, right? We had a lot of positive charge building up, but some negative ions come in, and now this bit is neutral. Right? Hopefully that makes sense. And exact opposite here. So here we had some copper 2 plus ions. Recording sorted, thank you. We had some copper ions. These got stuck to the cathode, and then we started losing positive ions. There's now less positive ions in the solution, right? They're getting consumed into this. Ions being released in concentration. They will. No, no, no. It's not. It's completely fine. Don't worry. What's the point of ions being released into the solution? So earlier here, the zinc is giving away its electrons. Zn2 plus is building up here, right? It's becoming it's too much positive, right? So the ions, the negative ion will go here, and it will make sure that this stays neutral. It is no longer excessively positive, right? Um, the reason we want the charge to be neutral. Is up salt bridge? No, NO3. No, it's definitely NO3 minus going down the salt bridge. Um, I wish I did galvanic instead of titration. Yeah, galvanic's really good for the IA2. What if you don't have a salt bridge? Good question. If you don't have a salt bridge, imagine this salt bridge didn't exist. Slowly, this would build up with Zn2 plus. Negative ions go towards anode. Thank you. Slowly, this would build up with Zn2 plus. This would become really positive. Look how many positive ions there are in the solution. Now these electrons, they're getting attracted to the positive bit, so they don't want to go anymore. They would just stay here. The electrons wouldn't move. So if we didn't have a salt bridge, the galvanic cell would work for a little bit, and then after a while, it would just stop moving. Yeah, become non-spontaneous over time if no salt bridge. Exactly. Positive. I don't know what that is. Okay. Hopefully that is fine. Does the salt bridge make sense to everyone? Is that cool? Okay, okay, okay. The last thing with galvanic cells is always KNO3. No, you can use any ion. You can use any salt. Oh, I'd never even heard about that. You can use any salt. This one is potassium nitrate. You could use I can't even think of it, like sodium nitrite probably. Anything works. Any salt works. Um, why do we both have bonds with NO3 then? I'm not sure what you mean. Anyway. The last thing at the bottom. Yeah. So I guess I probably should have started with this. It's pretty unimportant, but in here, right? I said that there were already Zn2 plus ions that existed in the solution. The reason Zn2 plus ions is because this is a zinc nitrate solution. That's kind of it. This is a zinc nitrate solution, so there's zinc 2 plus, and there's actually also nitrate ions. It's a zinc nitrate solution. So Zn2 plus. Yeah. And same thing here. This is a copper nitrate solution. There is just copper here, copper 2 plus, and just some NO3 minus. If you didn't have this, the charges would automatically be unbalanced. In a galvanic cell, cathode is positive, anode is negative. What if the salt bridge was nickel but had nitrate solution in both beakers? That's completely fine too. The point of the salt bridge is purely to balance charges. It doesn't really matter. Yeah. In galvanic cells where the solution may react rather than the electrodes, or is that the electrolytic cell? I'm not sure what you mean. No reactivity value? I'm not sure. Okay. Last thing with galvanic cells is that you don't have to do any calculations with this, but just so you know, okay, you guys, spoilers. Last thing is how come K plus goes to cathode if cathode is positive? The K plus is going to the solution, which is becoming increasingly negative because the Cu2 plus is reacting. positive ions in the solution are reacting to form solid copper, and so we're losing positiveness. There's positive stuff here, but it's going down. We're losing positiveness. And if we're losing positiveness, we want to put more in. What topics are left? Electrolytic cells, and that's it. Yeah. I'm trying to. I mean, I took a mini poll, and everyone said they wanted me to go on a little bit longer. Positive goes. Yeah, if you want to think about it like that, positive goes to the cathode is probably a better way to say it. Because saying positive goes to positive feels very counterintuitive in my head, but yeah. Yeah. Last thing I wanted to say is zinc. Remember, the zinc is reacting to release its electrons. It's turning into ions, and because it's turning into ions, it is literally losing metal. If you've ever done this experiment, you'll see that the zinc starts like corroding almost. It loses some of this mass, right? So one experiment that people do is they will do this experiment and then they weigh the anode and cathode. These are electrodes. I'll use that word, electrodes. They will weigh these and they'll find that the mass has actually gone down. Cool. I think that's it for galvanic cells. Anything else I want to say? Oh, the other thing I want to say is each of these are called half cells. That's something you should know. Half cells. Yeah. So the anode, this is the anode. The anode would lose mass because it's giving away electrons and it's turning into this. In this example, not always, it's giving away electrons. Whereas this, it will gain copper because the copper is becoming solid. Okay. Each of these are called half cells. That's just a term. Nothing special. This is a half cell. This is a half cell. Right? We can mix and match half cells. So if I had maybe this wasn't copper. Maybe I had bromine or something. Can I still see you? Oh no. The solid have to have the same number of ions as the electrodes. If it has less, it will run out and the charge accumulates. This system will stop eventually, right? We cannot have infinite power. It will stop eventually. That's inevitable. So how much you have is how much you have is just purely dependent. Identifying anode and cathode products. In this one, I guess I will show the yeah, I will I guess that's on the next slide. So yeah. Cool. I'll keep going. So each of these were half cells. I said that. And what if I had different half cells, right? These show you all the different ones. So maybe we want to use copper. Oh, that's wrong copper. This copper and this lithium, right? Access to PowerPoint. Yes, you will have access to PowerPoint. We've been going for a long time. Let's say we had lithium and copper, and let's say I wanted to know. Do I have an example in the next slide? I don't. That's a problem. It's okay. We'll just do it from here. Lithium. This is one of the sides. Yeah, it's diabolical. Muzz, we just kept going, and then I took a mini poll, and they've said they want me to go slower to cover everything, and just cop the fat recording length. Oh well, you're still getting a dentist fan. That's true. So yeah, we said the one that's more reactive, the one that's more reactive will want to get reduced. So how do we figure that out from this table here? This is what you use for galvanic cells. What we will do, let me get a highlighter. This in the top left or top right, this is the strongest oxidant. No, I'm Wrong word. Strongest reductant, right? And then this is the, I don't really have space, but it's the strongest, I'm just going to write over it, strongest oxidant in the bottom left. Let's start with just this one. Strongest reductant is this. As I go down this table, I can't even, okay, this is strongest reductant, right? As I go down and down, these become weaker and weaker reductants. So this is weaker than lithium. Barium is weaker than potassium. Calcium is weaker than barium. Sodium is weaker than calcium, etc. These get weaker and weaker, all the way until fluorine ions are the weakest reductant on this entire table. This table is on the formula sheet. Yes, yes, yes. Right? Then let's go the other way around. Actually, I can leave that. I can leave that. Never mind. I can't undo. That's fine. This right here is the strongest oxidant. As I go up and up, these become slightly weaker. So permanganate ions are slightly weaker. Dichromate ions are slightly weaker. Chlorine gas is even weaker, etc. They get weaker and weaker as an oxidant. Right? Remember, an oxidant wants to undergo reduction. Jojo, we are in fact still going. Reductant and reducing agents are the same thing. Yeah, reductant and reducing agent. A reducing, oh, well, I don't know. A reducing agent wants to undergo oxidation. And then an oxidant wants to undergo reduction. If I look at this, Li plus ions cannot undergo oxidation. They have no electrons to lose. They're already an ion. The only thing is they can do is gain. That's another thing to know. So, with all that being said, in my example here, what would happen if I had these two half cells? Well, lithium here is the stronger reductant. This is strongest reductant, actually. This is the strongest reductant. Cu2 plus, where is that? Cu2 plus is over here. This, of the things I have, this is the strongest oxidant. So it's the strongest oxidant of my example. So we have lithium and my copper. If you look at these species, let me get a different color so it's easier to see. This is the strongest reductant. It's in the farthest top right, or furthest top right. This is the strongest oxidant. It's in the furthest bottom left. So the flow of electrons, if I rub all this out, for electron will go from this to this, right? I'll do another example at the very end if we still want. Top of the table is more likely to reduce the bottom table. The top right of the table is more likely to oxidize. Hence, because it's the most likely to oxidize, it's the strongest reductant. This one, F2, is the most likely to undergo reduction, so it is the strongest oxidant. Yeah. Yeah. Cool. With that sorted, it's broken. Good luck. This is very confusing. Tell me which half equations are favored. No, I really just remember top right, bottom left. Top right, this one, the only thing it can do is give away electrons. So this is the top right one, this is my choice. And then bottom left one. This is the only thing this can do is take in electrons. That's all it can do. So it wants to go this way. Top right and bottom left. So yeah. Okay. Hopefully that makes sense. Anti-clockwise rule. I'm not sure about that. Oil rig, top right, bottom left. Of the species you have. So in this case, I was talking about these two equations, and this is the top right one, and this is the bottom left one. The last thing that I want to get very clear, there are some assumptions that we make to create this table. 1.5 equation, yeah. There are some assumptions we make for this table, and you should know them. They are quite important. One of them is literally written right here. The temperature is 298 Kelvin. That is an assumption. Another one, yeah, STP. Another one is the pressure is 1 atmosphere, which is 100 kilopascals. And the last one is the concentration of all of these, because some of these are like aqueous, right? The concentration is 1 molar. This is called STP, which is standard temperature and pressure. Standard temp and pressure. You need to know those. Stoichiometry calcs for externals? Maybe? Yeah, no, yeah. It's assumed knowledge, so yeah. Okay. Cool. Is everyone okay with up to here? Is everyone fine with that? We have kind of slowed it down a little bit, but that's okay. Cool. The last thing, I'm about to rub this out. So if you want to take a screenshot, go ahead. Give it a couple seconds if you want to get a screenshot. Okay. Let's rub all this out. Thank you. I want to talk about one other thing with this table. Okay. So you may have noticed on the side, we have these E naught, or we say like E degrees. I read that as E naught. E naught. I'm not going to write that. E naught. These are voltages, right? These are all voltages. So negative 3.04 volts, etc. Right? What these are is, remember in this example we had a voltmeter here? It was measuring the potential difference between this one and this one. What these voltages tell you is the potential difference between the hydrogen cell. This is the hydrogen cell, the hydrogen half cell, right? The hydrogen half cell. You have a cell notation? Yes. The hydrogen half cell and anything else. If the voltage is negative, then the reaction isn't spontaneous. Solutions, if you want to, yeah. There is a Nernst equation. Nernst equation isn't syllabus though. Kind of forgot it. It's been 3 hours. Yeah, I might have to. I don't know. Then we also have, so it's with any of these, and this tells you the voltage produced, right? When connected to the hydrogen half cell. Chem class binge watch marathon. So yeah. Is that clear with everyone? And so what we can do is we can just kind of like, if we want to figure out the, for our example, this is our zinc copper example, we can figure it out like this. So if we want to know the voltage that is produced from connecting these two half cells, right? if we want to figure out the voltage from connecting these two half cells, all we need to do is find the difference between these. So the E cell is the voltage for the whole cell. I've seen people write the formula slightly differently. So I don't know if I want to give you a specific formula, but in this it's like E cathode minus E anode. So I've seen different formulas, but the idea is the E cathode. Cathode is the copper half cell, and copper half cell is plus 0.34, plus 0.34, minus the E cell of the anode, and this is our anode, and so it's minus negative 0.76, which equals 1.10 volts, right? Rash has a question. What's the question? Did I miss something? Um, what's the molten electrolysis? I will. I'm not up to molten yet. What's a redox reaction? Don't worry, there's a recording for you. So this is our E cell value. We can do this with any half cell, right? I realized I did not show a special diagram for some of the different types of half cells. There is maybe if Panda, if you can get a diagram of like the hydrogen half cell, and the Cu2 plus Cu plus, basically just aqueous to aqueous. If you get send images of the half cells for those, that would be appreciated. Yeah, hopefully he can get to that. And while he does, I will move on. So in this case, we were looking at these examples where we converted chemical potential energy into electrical energy, right? But what if it was the other way around? What if we had two reactions that didn't want to occur, but they did, right? So this is a reaction that is not spontaneous. Spontaneous just means it happens by itself, right? Yeah, thank you. So if you guys look at those images, that is a hydrogen half cell. In our example, here, it looked a little bit different because we had a metal electrode. In this case, because the hydrogen half cell is, you can see the equation here, 2H plus 2E minus to H2. So 2H plus 2, 2E minus plus H2. In this case, we have a hydrogen gas getting pumped in. Hydrogen gas is getting pumped in here. And then it is going into a solution here. This is a solution of H plus ions. Yeah, solution of H plus ions. That is what they're not all the same this type. Some of them are gases, so we have to pump in gas instead of just having a stick of metal. Okay, back to this. What if we have a non-spontaneous reaction? What if we had potassium metal and we had lithium metal, right? And it just doesn't want to react, right? This shouldn't be possible. But what if we made it possible? What if we forced it to happen by giving it the energy it needed to react? And so the way we do that, potassium metal, lithium metal, this is donating an electron, this is gaining an electron. We want to give it the required energy perfectly so it can react accordingly, right? So here we have a molten sodium chloride, and it is electrolysis, right? I don't actually have the B cells, so I'm going to just quickly steal it. Where can I find it? If someone could tell me the voltage required, that would be appreciated. What's the threshold for spontaneity? HNaOH. What do you mean? Does anyone know the E cell? No. Okay, I'm gonna just find it, so I don't have to calculate. Give me 1 second. I feel like no one's got an answer. I'll find it later. I don't want to hold us up too much. So what we have is we have a battery here. The amount of voltage required Voltage required. But I'll keep going, and hopefully someone can find it. So here we have molten sodium chloride. There is no fluid. It is just, isn't it just positive? I just want to know the number. Here we have molten sodium chloride. The only species we have is Na plus and Cl minus, right? What happens is we have a battery, and now I learned it in different ways. The way I learned 1.23. Okay. I learned it in different ways. I want to say the way that I learned, and then whatever you guys want, you don't have to learn this, but this is the way I learned. Imagine these. If you guys do physics, you'll probably be more familiar with this. These are parallel plates. And what a parallel plate is in parallel plates, we have an electric field. I don't want to get too much into physics, but the idea of an electric field is there is like a force of attraction. So this is a battery. This is the positive end of a battery, and this is the negative end of a battery. Batteries have a positive side and a negative side, right? So this is a positive terminal, and this is a negative terminal, right? It's connected to the negative end, this is connected to the positive end. And an electric field is just it's like a magnet field almost, like a magnetic field, where if I had like two magnets north-south, obviously the south pole wants to point to the other north pole. I'm sure you guys are familiar with that. Very similar thing here. It's an electric field, so it is in just one direction, right? This is an electric field. I'm describing these electrodes as an electric field. And the reason I've said it is because in an electric field, the Cl minus ions, even if they're somewhere in the middle, they still feel a force. There's always physics behind chem. There's a force of attraction of the Cl minus. It's in an electric field. It wants to go towards the positive side. This is a positive thing. If the electric field stuff is confusing you, all you have to know is negative chlorine ions wants to go to a positive electrode, and it's positive because it's connected to the positive end of the battery. Exact opposite for Na plus. Na plus. This is the cathode is negative because it's connected to the negative end of the terminal. The positive sodium wants to go to the negative electrode, right? For the people doing physics, like a more technical explanation, obviously we don't have when we connect to a battery, it's not like this suddenly magically become positive. What happens? We get an electric field between them, and in an electric field, the positive charges want to move through the field, and so the sodium navigates towards this. That is basically what's happening. Cool. That was a bit of physics gap, but all that matters is that Na plus goes to the cathode, Cl minus goes to the anode. Cl minus. Didn't someone want to get pinged when I get to molten sodium chloride? I don't know if you guys pinged that guy. I forgot who it was. Oopsies. The Cl minus, it will give away its electrons, right? That is basically what this battery does. The battery is forcing a flow of electrons. Hopefully you know that. Batteries, or a circuit, is a flow of electrons, right? So the electron, the negative chlorine ion, it will donate the electron. It'll sit here. It'll give the electron to this, and the electrons will flow through the circuit. They'll go through the battery, and they go over to this side, where the sodium atom will pick up the electron here, right? Hopefully that makes sense. I think that's kind of it. Does that make sense with everyone? Is that pretty clear? It is being recorded, don't worry. Does this molten sodium chloride make sense? Cool. And this E cell potential, the way I figure this out is we have the reaction Na plus plus E minus forms Na metal, Cl minus releases it to form Cl gas. The E naught values for these, I'll do it in a table format because of space. E naught. So molten means that H2 or O2. Yeah, there's no water here. There's no water at all. Yes, no water at all. Where is it? So Na, this is negative 2.71, and then Cl minus over here. I'm getting a different number to, I don't know who gave me this, but I'm getting a different number to that according to this. But I'll redo it with my one. This is negative 2.71. Okay, thank you. And this is positive 1.36. Yep. These are the E cell values for my two half equations, right? For my two half equations, and then to find the E cell, or it's not even E cell, it's a required voltage. The voltage required, right? Voltage required is the E of the anode minus the E of the cathode, which equals positive 1.36 minus negative 2.71, which is, let me try and do that in my head, 4.07, positive, or 4.07 volts. So yeah, that is the required voltage for this. Sorry, I had the wrong number up earlier. Okay. Is everyone cool with the that molten sodium chloride and how I got this E cell value as well, or the voltage required? Yeah, it is gone over time. Electrifying similar electric plating? No, it is not. Cool. On to dilute sodium chloride. What is molten? Molten means liquid. Like imagine I took salt and it's not even aqueous, it's melted, right? Like I melted metal, but I'm melting sodium chloride. Are those half cells on SEP? Yes, they are. Let me. I kind of already circled them here. Na plus, Cl minus. There you go. Cool. So there are a couple cells you need to know. One of them is molten sodium chloride, and I just covered that. That's the most basic example. You also need to know dilute sodium chloride, concentrated sodium chloride, and copper sulfate. Yes, sorry. Yeah. Notice I flipped the order. This is the voltage required. It should be negative, right? And because it's negative, it's not spontaneous. That's why it needs 4.07 volts in order to work. Okay. So, dilute sodium chloride. Let's try and figure out what happens here. This one is a fairly basic example. Let's think about in the solution, if it's dilute sodium chloride, what do I have? These are inert electrodes, by the way. Did I write them on the previous slide? Yeah, I did. Electrolytic cells non-spontaneous? Yes. That was this slide. They are not spontaneous. So, an inert electrode, sorry, I didn't mention this earlier. Inert electrodes just don't react. They are inert. They have no reaction. Typically we use platinum or we use graphite. Those are the most common inert electrodes. So, here we have an inert electrode. Let's think about what species are in this solution. So I have what? I have Na plus, I have Cl minus, and I have. Especially we want to know what ions. Let me write that. What ions? Because there's some water in here. Na plus, Cl minus. So Na plus is there, Cl minus is there, but H2O can self-ionize, right? So we want to consider that too. From the H2O, we're also going to get H plus, and we're also going to get OH minus. So let's write those down too, because those are important. Cool. Sorry. So from these ions present, let's just write all the half equations that are possible. So this is all the half equations that are possible with these ions only on one side. So you can see here we have Na plus with some electrons. Here we have H plus with some electrons. Here we have OH minus on the right, and we have Cl minus on the right. Firstly, can anything spontaneous happen? Let's have a look. So these are all the species that are present, right? Remember I said the rule of top right and bottom left? Well, the top right thing, technically it's this, but this doesn't exist. This doesn't exist either. So the top right thing is 4OH minus. That is the top right thing that we have in our thing, in our solution, right? Then let's look at the bottom left. And in the bottom left, we don't have this, we don't have this, so we are left with 2H plus. This is not a spontaneous reaction. Top right thing again. So I said a spontaneous reaction occurs between, for all my solutions, or for all my thingos, between the top right and the bottom left. This is the strongest oxidant, this is the strongest reductant. Sorry. This is the strongest reductant. Sorry. This is the strongest oxidant. That's my bad. Right? That is how this works. This would react, right? But we don't have those elements. How do we know when it's spontaneous? Spontaneity is by what's it called? Spontaneity. Okay, I don't want to have to go over everything I said earlier as well. A reaction is spontaneous if we have a stronger reductant than oxidant. Yeah, it's 9:30. I don't want to keep repeating. That's my only concern. Hopefully someone can give a good explanation for when it's spontaneous and not, so I can keep going. Yeah. So, all-nighter. Yeah, so hopefully someone can explain it. Let's keep going. In this case, this is not spontaneous, and because these two are opposite, right? So we will provide just enough energy for a reaction to occur. And that amount is this, right? This is the smallest energy difference in order for a reaction to occur. Do I have an example? No, I don't. So what happens is we have, in our solution, we have Na+, we have Cl-, we have OH-, and we have H+. According to our thing, this is positive, this is negative, so this is positive, this is negative, right? If available, yeah. If you look at this, what will happen is, if I provide 0.4 volts here, then the negative OH- ions will give its electrons away here. These will go through the wire, and they'll go to this side, to the H+, and they will get absorbed by the H+. This is the smallest difference, right? I know there is Na+, but the Na+ just doesn't happen. The Na+ is too far away, or not too far away, as in the potential difference is very big. 2.71 versus negative 2.71 versus 0.4. This is a big difference. We want to just provide enough energy for the easiest reaction to occur. Right? So yeah. Does that make sense to everyone? That this is the smallest potential difference between these two. So if I give just 0.4 volts, we can have a reaction occurring. Because, yes, whatever requires least voltage input. Even if I give more voltage, we probably want to do the easiest one first. In most cases. Is by definition electrons that are inert? Yes, the electrons are always inert. What about the other water half equations? This isn't a half equation. This is an electrolytic cell. Half equations are only for galvanic cells. Okay. So, hopefully that makes sense. What will happen is these two reactions will occur. The H+, let's say 4OH-, will give its electrons away. It'll produce O2 gas, water, and then it releases electrons. These electrons are taken in by my 2H+ to form H2 gas. If I'm to write the final balanced version of this reaction, I would get, let's just write it on the side here. I have to double this one by 2, this whole reaction, in order to get 4 electrons here and 4 electrons here. Remember, this is the theory from earlier. So I get 4H plus 4OH minus reacts to form 2H2 plus O2 plus 2H2O. That is my balanced redox reaction. Okay. Hopefully that makes sense. We have concentrated solution, sodium chloride, right? Concentrated sodium chloride, all of the ions present are the same, right? We still have Na plus Cl minus, but something different happens here. And you kind of just got to know that. There's nothing more I can say. Do you simplify the factor of 2 from before? I took the 2 times. The 2 times went on this to produce, produce this 4 here. And I went on the H2 to produce 2H2. I don't know if that answered your question some. But yeah. Okay. So, concentrated sodium chloride? No. Yeah. There's U2. Concentrated sodium chloride. We're almost at the end, guys, I swear. Concentrated sodium chloride. The ions present are the same. There's still these and there's still these. I'm not going to rewrite them. You kind of know them already. But something different happens here. And it's... Oh, wait. Some of these numbers are wrong. Sorry. This should say 0 volts. 0 volts. This should say... plus 0.4. 0.4 volts. Sorry, guys. Wrong numbers. My bad. Okay. Something interesting happens in concentrated sodium chloride. In concentrated sodium chloride, the amount of Na plus ions and Cl minus ions is a lot. They will end up greatly outweighing how much H2O there is. So how much OH minus and H plus. There's barely any compared to how much H plus and OH minus. So something really important happens here, and this is just something you got to know. In this reaction, this will still be favored, right? But the Cl minus will be favored instead of the OH minus. Why? Because the amount of OH minus is nowhere near the amount of Cl minus ions in the solution. That's really important. So instead, the reaction will only occur between 2H plus and Cl minus. I've kind of just like ignored the chat that's like not pings for me. Or Panda. So yeah. The reaction will occur between 2H plus and Cl minus. That's just something you have to know. Right? The super important thing is in our dilute example, it was just these two that are adjacent, because that is the smallest difference, right? The important thing is this the reason why the limitation of electric potential is it needs to be 1 molar. That's a good question. Panda, can you get on that? Okay. That makes sense. That makes sense though. Cat Trooper's question. The one Voral responded to. I think it's right. That for concentrated NaCl, it is an exception because it's not like the other one because we've assumed. That makes a lot of sense. I would agree with that. I'm actually going to steal that explanation as the reason. Like, what do you mean we're still in Unit 3, DN? I'm only doing Unit 3. I think you're trolling, but... How do we know when to assume, when to not? The assumption of the SEP table, all this data that you've gotten, is assuming that it is 1 molar. So for that reasoning, maybe you actually can't use these numbers. That's actually a really good point, and I've never thought about it until now. So assume that's not true. Those numbers don't exist. That's a really good point, and I've never thought about it. Molten can't even be used? Ah, because it's not, these are assumptions. Yeah. Guys, oh, I can't even write anymore. I want to apologize and take back my calculations. This one's only true if it's 1 molar, only if 1 molar. This one is a lie. I apologize. I will fix that in the PowerPoint slide before I release them. That is a really good point. That these are only for the assumptions that we had. And because we're not satisfying the assumptions, you can't use this. Thank you for forgiving me. Why not? I think the why not, because it is a aqueous solution. If the concentration is 1 molar, that means it has to be in solution. Oh, and temp's probably too high too. You don't have to memorize, you don't have to calculate this. But you do have to remember all these for the sake of it, yes. I want to apologize for this. My bad, guys. Okay, that's gone. Imagine I didn't have any numbers here. No calculations. Aqueous 1 solution? Yeah. This is what they expect. Yeah. Why aqueous solution? One of the assumptions of this table, because remember, I was getting all my numbers from this table. This table makes some assumptions. The assumptions are 1 atmosphere, or 100 kilopascals, same thing. It assumes 1 molar concentration, and assumes a temperature of 298 Kelvin. Need to finish electrolytic. I mean, I'm on like the second last one, so yeah. So yeah, when we have concentrated sodium chloride, there is a lot of H plus, a lot of Cl minus. So the Cl minus ends up hogging the electrode instead. And so what happens is a reaction between these two will occur. So I will have 2H plus 2E minus forming H2, and I will have Cl2 plus 2E minus forming Cl minus. Oh yeah, I should probably write it the other way around. My bad. Cl minus, just so you can see it easier, Cl2 plus 2E minus, and these electrons go straight into the next one, 2E minus plus 2H plus forms H2. So the full equation would be Cl minus plus 2H plus forms Cl2 plus H2. Cool. How do we know what happens? You can still figure out what happens because these equations are still true. The only thing that's not true is these numbers. These numbers are different. But you know these reactions are true. Like this reaction can occur. But these numbers might be different, so you might have to reorder them as well. It is pure theory that you should memorize. Yes, the reactions still occur. Yeah. Cool. Last one, aqueous copper sulfate. I didn't have a slide for this, or a slide on the next page. Oopsies. Copper sulfate. Let me put the formula sheet. Sorry, guys. One more thing. So we have Cu2 plus. Let's write it. Cu2 plus 2E minus. I don't know why I don't have a slide for this. That's also my bad. E naught is plus 0.34 SO4 2 minus cannot react at all. There is no reaction for it. Someone correct me if I'm wrong. I don't think there's any reaction with SO4 2 minus on its own. It is the longest class ever. I want to be free. And then we also have H2O. So we have H plus, OH minus. I am probably going to skip this for time. This is standard. There's nothing special about this. You can just do this as normal with all your theory from earlier. Yeah. I think the very, very last thing is electrochemical plating and purification. 4 hours now. What's a harder example? By standard, I just mean like you can figure it out from theory. The concentrated sodium chloride you have to memorize, right? You won't know. You couldn't. There's no way you could just figure this out on your own. You have to memorize it. This one you can do all the calculations for. It's as normal. In my slides, I will fix up copper sulfate and I will post that. But I will finish electroplating and then hopefully we're finally done. Electroplating. There's a nice QCAA question. If I can find it, I will send it, or if someone else finds it, they can send it. But the idea of electroplating is we have some impure copper here. 7 different copper sulfate, aqueous sodium chloride. That looks like dilute sodium chloride. Someone else answer that. By someone else, I mean Panda. Electrochemical plating. Here we have some impure copper. There's some impurities. I don't know what. Here we have pure copper. In this, we will have maybe like, I don't know, a bunch of metals. Let's say one of them is, oh, I'm not done. One of them is Cu, and then plus some other stuff. I don't know what else. What will happen is, think about iron, sure, whatever else. There's a nice question. I'll send in the chat. The copper will give away its electrons. You can see this is positive, this is negative, negative, positive. Electrons flow this way. This is the flow of electrons. So the copper here, we have some copper. It is solid. The copper will give away its electrons. So electrons will go here. And we give just the right amount of voltage. I don't think you have to do any calculations with this because this is like hard to figure out. Like you don't know what impurities are in here, right? But we give just enough voltage that we can cause this copper to give off its electrons. So this will turn into Cu2 plus ions in the solution. And finally, the electrons come around to here, and the electrons attach to the copper ions here. So this will get copper. This will grow bigger because copper metal is starting to attach. We get on one side Cu S forms Cu2 plus 2E minus, and on the other side we get the exact same reaction in reverse. Basically, we have impure copper. We take just the copper bits, and just the copper bits turn into the solution. And then just that solution will become stuck onto the other metal. You can do that with lots of different metals, and when you do it with a different metal, this is refining, actually, the example I just said. But if you do it with a different type of metal, you can plate instead. You can do copper plating. Or not copper, you can just plating with any metal. Positive terminal on the battery decides it. Yes, yes, yes. Electrolysis, yes. Yeah. Are there any questions with that? I know I went through that fairly quickly in the interest of time because we've gone very over. Is the pure or impure cathode? what's up? What's the right amount of voltage? The voltage required is the voltage required depends on the impurity of copper. I don't think you will have to do any calculations with this. Yeah, not syllabus in this context. Sorry, yeah, I missed it. Appeared to be cathode, yeah. Isn't impure the anode? Yes. Why is impure the one removing? We take this. This is an impure mix of copper. Impure just means it has a mix of lots of different things. But I am putting it in solution because it is losing electrons, but only the copper. So let's say in this let's say I had copper and I had iron, right? I'm going to give just enough energy in this battery. This battery is just going to be the right amount of voltage so that the iron cannot do this. It cannot turn into ion form. This reaction cannot happen, but this reaction can. This reaction can happen. How do we know for sure that it can't turn? It depends on the energy, the voltage you use. What if the impurities require? So you can't do this with lithium. Wait, let me do one at a time. Oh, that one. That one's A, not syllabus. B, I think it's BS Chem. Like, I'm pretty sure they're wrong in the answers. That is NEEP 2022. I know that now. NEEP 2022. It's the second question. Um, it's out of syllabus. The answers are wrong. It doesn't make sense. Um, yeah, I'm pretty sure the answers are wrong. I showed my chemistry teacher this question, and I asked him directly. I'm like, "What is this?" And he told me those words exactly. He said, "It's fake chem. The answers. It doesn't make sense. It's out of syllabus. Don't worry about it." Yeah. I missed some questions further up. Let me try and get back to those. What if the impurities require a lower voltage to oxidize? That's a great question. Let me find an example. Actually, finding an example is going to be very tricky. Um, yeah, and then I got another question about lithium straight after. So, um, I was talking about the one, yeah. Um, I was okay to to answer your question. I wish I had an example for you. I'm going to use this slide. I'm not free. That's very ironic that I'm using this slide for working. Um, so I have two things. One of them's impure. If one of them, zinc and magnesium as impurities, yeah. If one of them like zinc and magnesium, whatever, right? Or even if I had lithium, if I had a battery here, if the battery had enough voltage to allow, let's say this is supposed to be copper, right? If and there's a lithium impurity in it as well. Sorry. If there was a lithium impurity, then if I had enough voltage, the lithium would go into the solution, right? It'd become lithium ions, and there will be copper ions. Sometimes that is possible, but if lithium is capable of turning into ionic form, it's not capable of solidifying onto this electrode. Yeah, it is not capable of going on the electrode. If it can dissociate into the solution by giving away electrons, it can't go onto here. Only copper can do both. Yes, caveat is voltage is not too high. Thank you, Scorpius. Scorpius is also incredibly smart at chem. The question Johannesburg sent is not syllabus, no. I'm done. Um, Is this assuming the pure electrode? Yeah, I'm gonna go back to